The first order of business in today's ECH 4123 class is to clear up a very serious mistake I made from Monday's class. So this was class number 15. And maybe you noticed when I was doing the video that I confused myself a little bit on the first day back from the summer break. And thank you to the students who pointed this mistake out and prompted me to start the video by doing a quick little recap. So on Monday's class, I had a little sentence that says, as temperature goes up, what happens to the mole fractions in the vapor and the liquid phases? And I incorrectly said on Monday that as temperature increases in general, XA and YA will also increase. This is why it's incorrect. So this is what I was trying to say during our synchronous session on Wednesday, but hopefully these diagrams help clear it up a little bit. On the very left-hand side, this picture denotes a system of benzene toluene at the bubble point. So I just chose a certain composition of benzene toluene. I chose 60% benzene, 40% toluene completely arbitrarily. And because it's at the bubble point, I should have filled this cylinder all the way up with liquid, but that would be unrealistic. All it means is that this vapor phase, or this headspace, is mostly empty. There's just one bubble of benzene toluene. However, that one bubble is 81% benzene, 19% toluene. Now, where did I get these numbers from? I got them from the TXY diagram. So this left-hand diagram is represented by this bottommost tie line right here. So at 87 degrees C, which is about like there, I'm drawing my blue tie line across and I'm reading off the compositions. So here's where I got 60% benzene, 40% toluene, which was arbitrarily set again, but the point is that at the bubble point, the liquid phase composition is unchanged from the overall system composition, and that is because a vast majority of the system is in the liquid phase. Remember, there's only one bubble of vapor. I don't know how to accurately draw one bubble that is 81% benzene, 19% toluene. Just remember that a molecule is very, very small, right? There's 10 to the 23rd molecules in a mole, so that you can have one bubble with multiple molecules in it, and that one bubble would have 81% benzene molecules, 19% toluene. And then, of course, this is where I'm getting the 81% benzene from. Now, if I increase the temperature a little bit more, say to 92 degrees C, now I've got a little bit more vapor forming, and I've allowed the system to come to vapor-liquid equilibrium. So at 92 C, I draw another tie line, and that's the middle blue line there, and I can read the compositions again. So I'm saying that that is 49% benzene, and this one is 72% benzene in the vapor phase. All right, so importantly, XA and YA have both gone down, and it's important to note here that this is only for the more volatile component. So that's typically how my brain works, but if for whatever reason we're talking about the less volatile component, it reverses, right? So you have to specify, or you have to have an understanding of the convention of which component you're talking about. So what I mean there is that YA was 81% benzene, now it's 72% benzene. XA was 60% benzene, now it's 49% benzene. That trend will continue to increase. So if I increase the temperature even more, to 95 C, now I've got more and more liquid evaporating, so there's a greater percentage in the vapor phase. And my compositions are now, they're about the same, they're flipped, so don't get confused. This is the 37% that I'm talking about for benzene, and this is the 62% benzene that I'm talking about. So again, it went from 72 to 62 and went from 49 to 37. Now, how does this make sense? This is the way I rationalized it in my head. So as temperature is increasing, the more volatile component is evaporating from the liquid phase more readily. That part I hope makes sense. The more volatile component should be leaving the liquid phase more readily than the less volatile component. Therefore, the composition of the more volatile component, XA, should be decreasing. The one that doesn't really make sense is why the composition in the vapor phase also decreases. So why does YA decrease if the more volatile component is leaving the liquid phase? It should be going into the vapor phase at a greater rate. And that is because it is becoming more and more diluted. So here's another analogy that I thought of. And this comes from when I was in high school. My mother was involved in local politics, and we'd be sitting at election day. We'd be watching the results. And when I was looking at the results and I found my mom was up in the election, I think she was winning 54% to 46%. And somebody said, oh, wow, that's a landslide. And I said, well, that doesn't sound like a landslide to me. And then I looked at the mathematics a little bit more. So let's just say that there's an election with two candidates. So you've got candidate A and candidate B. And let's just say there's one polling station. And let's say we are sampling after the first 10 votes. So after the first 10 votes, let's say that 7 people vote for candidate A and 3 people vote for candidate B. And then let's say another 10 votes go by. After 10 more votes, you know what, let's make it more lopsided because it'll be more illustrative that way. Let's say 9 vote for candidate A and 1 vote for candidate B. After 10 more votes, let's say now that 6 vote for candidate A and 4 vote for candidate B. So after 10 votes, you would say that because 9 people voted for candidate A has a 90% advantage. After the second 10, but they also has an 8 vote advantage. So I want to make that distinction between the percent and the amount. So the lead here is 90% or 8 votes. After 10 more votes, the total is now 15 versus 5. So candidate A has gone up, right? So candidate A is now up by 10 votes. But what is the percentage? It's now 15 divided by 20, or 75%. So the idea here is that as more and more stuff evaporates, it's going to tend to come back to the midpoint more often. So in an election with thousands of people voting, 54% is actually a very significant amount if it's 1,000 people. So hopefully that clears up the rationale for why that is. And then also I want to clear up that the inverse is also true. So I could also say as P decreases, then XA would increase and YA would increase. And you could show that by the same logic using the PXY diagram, and also noting that component A is always by convention the more volatile component. So that is the first thing, and we're going to go on to something else. I'm just going to keep this video rolling. So last time we derived the equilibrium condition for mixtures. We said that the chemical potential of species I in phase A must be equal to the chemical potential of species I in phase B. So just again, I want to make sure I'd rather over-explain what the notation means than under-explain it, just in case there's any questions. So I is a component, so that is a chemical that is in the mixture. So for a two-component mixture, that would be the two components. And then alpha and beta are phases. So commonly when we're talking about phase equilibrium, we'd say vapor and liquid, for example. Right, so the chemical potential of a component is going to be equal in both phases. You can show with a short derivation that I'm going to skip in the interest of time that this equilibrium condition can simplify to, you could just as easily say that the mixture fugacity, so remember that's F hat, mixture fugacity of species I in phase, we're going to call it liquid and vapor here. So mixture fugacity of species I in liquid must be equal to the mixture fugacity of species I in the vapor. So again, these two things are the same expression with a short derivation that I will skip. And then recall that by the Lewis-Randall rule, the mixture fugacity of species I in the liquid phase is equal to the mole fraction of species I in the liquid phase times the pure component fugacity. This was again by the Lewis-Randall rule. And then you can capture deviations for non-ideal. So the Lewis-Randall rule is for ideal. And to capture non-ideal, all you have to do is add that activity coefficient. We showed that last time as well. So Xi, Fi, Gamma I. All right, and then by the analogous Lewis-Randall rule, also showed this last time, that for the mixture fugacity of a vapor, you could express it as the mole fraction in the vapor phase times the total system pressure. And then, so this is not the Lewis-Randall rule. analogy to Lewis-Randall rule. And this is again for an ideal gas. So I'll also say that this is in general. So this is for general non-ideal because I added the activity coefficient. Remember, the activity coefficient captures deviations from equilibrium. So I'm sorry, captures deviations from ideal conditions. So if the activity coefficient is 1, then I've got back ideal conditions. So I can capture deviations from ideal conditions in the vapor phase by saying the mixture fugacity of the vapor is YIP times phi I. And this is what we mean when we say Gamma-Phi modeling. So gamma and phi are the two deviations from non-ideal cases. And if we use the equating of the mixture fugacities and we plug in these expressions, we obtain the following. So we've got xi f hat I gamma I is equal to yi p phi I. And this should look vaguely familiar to our favorite modified Raoult's law. So again, if gamma and phi are both 1, we've got xi fi equals yip. And then if we further make the assumption that the pressure is low, so if pressure is low, then phi, I'll just write this out. One moment. So if I'm assuming low pressure, then phi is equal to 1 because it's that pressure is low signifies an ideal gas. So if the vapor phase is ideal, then I've got a phi is equal to 1. And then going all the way back to the Poynting correction, we could say that the mixture fugacity of component I in the liquid phase is equal to the vapor pressure. If we plug both of these things in, we get our modified Raoult's law back. Xi pi star gamma I is equal to yip. So hopefully that explains a little bit of where the Raoult's law comes from. I'm going to wrap up the first video now. I'm going to do one more video and then we'll do an example problem.